So two runners, A and B, they're running on a straight track for 10 seconds, and this graph shows the velocity of runner A at various times, and the velocity of runner B is given by a formula. All right, so we want to find the velocity of runner A and the velocity of runner B at time 2 seconds. So here we're just plugging in because the functions are velocity functions. So for runner A, I just go to 2 seconds, go up to the graph, looks like 7. So A of 2 is 7, and this is measured in meters per second. And B of 2, I'm going to plug into my formula. So it's going to be 48 over 7. And you can't reduce that. I'll just leave it meters per second. Okay, so now I want to find the acceleration of runner A and the acceleration of runner B at 2 seconds. So how is acceleration related to velocity? It's the derivative. Acceleration is the derivative of a velocity function. And so for a graph, if I'm trying to find the derivative at a point, what am I looking for? The slope of the tangent line at that point. So if I want the acceleration at 2 seconds, I'm looking for the slope of the tangent line. And what's the slope of that line? 3 1/3, yeah, 10/3. Yep, so we went from 0, 0 to 3, 10. Rise over run is 10/3. All right, I should name these differently. I'm going to call this the velocity of runner A and the velocity of runner B. And so then I'm going to do the acceleration of runner A at 2 seconds. That is 10/3. And what are my units on this? Meters per second squared, yeah. So when we did the slope of a line, this was a change in y over a change in x. And the y units are meters per second. And the x units are seconds. So it's meters per second or meters per second squared. All right, and then the acceleration of runner B at 2 seconds. Well, the velocity of runner B is given by a formula. So to get the acceleration, I need to take the derivative of that formula. And then I'll plug in the 2. So the acceleration of runner B at time t is the derivative of this velocity function. And what do I have to do to take this derivative? Quotient rule, yeah. So denominator times the derivative of the numerator, so 2t plus 3. Derivative of the numerator is 24, minus the numerator, 24t, times the derivative of the denominator, which is just 2, all over 2t plus 3 squared. And then I need to just plug a 2 in there. I could do a bunch of simplifying, or I could plug the 2 in and then simplify. So when I plug in a 2, I'm going to get 2 times 2 is 4 plus 3 is 7. 7 times 24 minus 24 times 2 is 48 times 2 is 96. And then 2 times 2 is 4 plus 3 is 7 squared is 49. $1.47. And again, this is meters per second squared. That makes sense? So this is old, right? So I'm trying to sort of take you back and take you forwards. It reminds you what we've done, and then we're going to talk about how to go the other way. So if you know velocity, you can take the derivative and find its acceleration. Or we could find the total distance traveled by runner A and the total distance run by runner B over the interval of time. So for runner A, the distance that runner A ran, that would be the integral from 0 to 10 of the velocity function, right? And the way you calculate the integral is the area under the curve. That's what the integral represents. So I can go up to my picture and I can find the area under this curve because it's just made up of a triangle and a rectangle. So I don't have to know any fancy integration rules. I can just find all this area. All right. So this rectangle part has a width of 7 and a height of 3. So its area is, yeah, 10. Thank you. Width of 7, height of 10. So its area is 70. And then this triangle, it has a base of 3 and a height of 10. And the area of a triangle is 1/2 base times height. So it would be 15. So the total area under the curve is 85. So just to, I'm sure we all know that this, because this is measuring distance, its units should be meters. But just to verify that, this is an integral of a product of two things, right? The velocity function, it's measured in meters per second. So this is the area of a rectangle, remember, it's representing the area of a rectangle. Its height is the value of the function, and dt is the width. And so this is dt, it's measured in time units, which is seconds. Meters per second times seconds gives you meters. So if you're ever in doubt about what an integral is measuring, do a little unit analysis. Okay, right, and then the distance that runner B runs, also the integral from 0 to 10 of the velocity of runner B dt. This one we're going to have to use a calculator because the formula for V is a curve. And to find the exact area under a curve, we have to use more and more and more rectangles, let that limit go to infinity, and our calculator can get a pretty good approximation of that. The actual limit calculation is really tedious, so we'll just do it in the calculator. All right, so math, int, type in the function, so 24x divided by 2x plus 3, comma x, comma 0, comma 10. Put parentheses around this numerator. It's like 83.3. Okay, so I'm going to leave this. We can come back to this if we have time. But you do have the answers to this, so you can tell if you are getting it. And if we don't have time to come back, you can come see me or go to the studio to get help on that. All right, so we're going to look at class 40. This is our last lecture. Next class, we do have class on Monday, and that will be a review for the final exam. Final exam is next week on Wednesday. And I will be here 8 to 3. So come anytime. I'll be in this room. Your official scheduled time is 8 to 10. I know you also have physics that day. So if you need some flexibility, you know, I'm here all day. You could come in here after, yeah. I'm giving my algebra final 1 to 3, and they, okay. So I sent out an email last week that we're canceling that quiz. No quiz today. Okay, so in this section, we're going to see a few theorems about definite integrals that should feel relatively straightforward, based on the definition of an integral as being the area under a curve. So if we think about the geometric definition of a definite integral, these should feel pretty straightforward. All right, so the first question we're going to ask is, what if the limits of integration are the same number? I want to find the area under a curve between x equals a and x equals a. How much area is that? None. Yeah, because there's no width to that rectangle, right? So a line geometrically has 0 area. So we define the integral from a to a of any function as 0. There's no area because there's no thickness to the rectangle. Okay, and then what if the smaller number, what if we put the smaller number on top? So we've always been putting the smaller number on the bottom, like the integral from 2 to 5, and that means the area under the curve between 2 and 5. If you switch the integral, the limits of integration, so we put the smaller number on the bottom, then you can just reverse them and make it look normal, right? So, and put a negative in front. So you can think of this rule as going backwards in time. So if you're to find the area under a velocity curve to get distance traveled, if I wanted to find the distance traveled between t equals 5 and t equals 2, it's like going backwards in time, so the distance traveled is like negative. The negative of what you would have traveled from 2 to 5. All right, so a couple of little examples to play with these two formulas. What's the integral from 3 to 3 of x plus 2 dx? 0. Don't even have to do anything, right? Because x plus 2, just a function that looks like this. And here's 3. So basically, I want to find the area of a line that has no thickness, so it's 0. Okay, so for b, I want to find the integral from 1 to 0 of radical 1 minus x squared, and I drew a little picture of what radical 1 minus x squared looks like. So my second theorem says that this integral is equal to the opposite of the integral from 0 to 1. Right, so my limits of integration look funny because we usually put the smaller number on the bottom. So because the bigger number's on the bottom, I'm just going to put them the way that I'm used to seeing them and put a negative out front of the integral. All right, and then I need the area between 0 and 1 under this curve. How much area is there? A quarter of a circle that has radius 1, yeah. So the area of a circle of radius 1 is pi, right? So this is pi over 4. So my answer to the integral that they gave me is going to be negative pi over 4 because they reversed the limits of integration. All right, so continuing to think about the geometry of areas, what do you think if we try to take the integral from a to b of a function that's the sum of two functions? Maybe we want to draw a picture of it. Here's f of x. Here's g of x. So what does f of x plus g of x look like? Yeah, yeah. Yep. So f plus g is a function where I add, so pointwise, I add the values. So if this were 5 and 10, f plus g would be like 15. Right? So f plus g, I don't have enough room to draw it properly. Okay, there we go. So I would add this distance plus this distance. That would be my f plus g distance. So it's going to be something up here, right, where I would add. So if I want to find the area under the f plus g curve, I can take the area under f and add the area under g, and I would get the area under f plus g. So you can take the two integrals separately and then add them together. Same with subtraction. And then with a constant, if you want to take the integral of a constant times a function, you can bring the constant outside of the integral. You can just find the area under f of x and then triple it or quadruple it or whatever you're multiplying by. All right, D is the least straightforward, but if you draw a picture of what it's saying, it is much more obvious. Okay, so this says that the integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to, and here's a picture, a to b are the endpoints, and I put a c in between here. If I take the integral from a to c, that's this area, right? And then add to that the integral from c to b, which is this area, what do I get? The integral from a to b. I just get all the area. So this is just the integral from a to b of f of x dx. And it's obvious when you draw it with c in between the a and b, but it actually generalizes to always be true, even if the c is outside the a and b. And I'll leave you to think about that on your own. Oops. And it has to do with the rule from earlier when you reverse the limits of integration, that integral actually becomes negative. So that's why this can still be true. Okay, so by hand, I want to evaluate the integral from 0 to 1 of 5 minus 3 radical 1 minus x squared dx. And we'll check on our calculator. Okay, so I'm going to use several of the rules here. This is the integral of a difference of two functions. So when I take the integral of the difference of two functions, I can separate them into two separate integrals. So this is going to be the integral from 0 to 1 of 5 dx minus the integral from 0 to 1 of 3 radical 1 minus x squared dx. And then the second integral is a constant times a function. I can bring the constant outside of the integral. Okay, so the integral from 0 to 1 of 5 dx. If I draw a little picture, that's just a horizontal line at a height of 5. And I want to find the area under that curve between 0 and 1. What is that area? 5. 1 times 5 is 5. Okay, so this is 5 minus 3 times this integral we calculated earlier, right? That is 1/4 of a circle of radius 1. So its area is pi over 4. So this is 5 minus 3 pi over 4 is the exact area, or the exact value of the integral. So let's have the calculator do the same integral and make sure it agrees. Math 9, and my function was 5 minus 3 times the square root of 1 minus x squared, comma x, comma 0, comma 1. When I did this integral, we did that earlier in class. The radical 1 minus x squared dx, that is 1/4 of a circle. With radius 1. So a circle that has radius 1 has area pi, right? Pi r squared. So then I just took 1/4 of it, pi over 4. Yeah, okay, so that's a really good question, and we ask it a lot. The dx, is kind of a leftover piece of notation from when we developed what the integral notation means, right? So think of when you're taking an integral, you're adding up an infinite number of rectangles. Each one has height, the function value, radical 1 minus x squared, and width, some small delta x, right? So the dx is there to represent some small width of a rectangle. But when you're finding the exact area under the curve, if you're not using rectangles to do it, this dx is kind of like, it's just floating around. It doesn't tell you to do anything, right? It just is a notational trying to think of like an analogous situation where there's a symbol. Yeah, it just represents the width of a rectangle and it's approaching 0. Yeah. I'm gonna try to think of an analogous time, but I don't have one off the top of my head. Okay, so let's make sure that this matches this. 5 minus 3 pi over 4. Yep, same value. So the advantage to being able to calculate integral by hand is being able to get an exact value as opposed to the calculator, which always has to estimate. So right now, if we're doing it by hand, the only time we can get an exact value is if we're dealing with a linear function or maybe a circle, because we have formulas to get those areas, triangles and rectangles and circles. All right, so I wanted to spend a couple minutes trying to answer these questions before we go over them. So, and I'm going to fix this diagram while you're working. All right, so they've given us the areas of these 3 regions, 1, 2, and 3 are 4, 10, and 7. So if I want to take the integral from 0 to a of f of x dx, that's the area under the curve between 0 and a, which is 4. Good. Right, and then the integral from a to b, so the area under the curve between a and b, -10, yes, because that area is below the x-axis. So when you take an integral, area below the x-axis counts as negative area. All right, area from B to C is 7. All right, how about the integral from 0 to B? -6, yep. So we have 4 plus -10. So the integral from 0 to A is 4 plus the integral from A to B, which is -10, gives me a net area of 6. Integral from A to C? Yeah, thank you, -6. -3, yeah, because we have 10 below the x-axis, -10, 7 above the x-axis, so my net area is -3. How about from 0 to C? 1. I have 4 above and 7 above, which makes 11, and then I have 10 below, which is -10, so my net area is 1. Integral from A to 0, what is that? -4. It's just the opposite of the integral from 0 to A. And the integral from B to A is the opposite of the integral from A to B, so it would be +10. And the integral from C to A, that would be the opposite of the integral from A to C, which was -3, so that's 3. All right, so now if I know the integral from 1 to 10 is 4, and the integral from 10 to 3 is 7, I want to figure out the integral from 1 to 3. So this one is written a little weird, right? 10 to 3. So if we flip the limits of integration so that we say, oh, well, the area from 3 to 10 would be -7. So this is actually area under the curve. So the integral from 1 to 10 of f of x dx is 4. And the integral from 3 to 10 of f of x dx is -7. So it should be that if we add the area from 1 to 3 to the area from 3 to 10, I should get the net area from 1 to 10. So like that out. I should be able to add the area from 1 to 3 to the area from 3 to 10 and get the area from 1 to 10. So this one is what they're asking me for. 3 to 10 is -7. So this we'll call this x plus -7 equals the integral from 1 to 10, which is 4, which means x has to be what? 11. So E. That makes sense? All right, so we can also use some basic properties of symmetry. If you're lucky enough to have some symmetry in the function you're taking the integral of, it can help you evaluate an integral. So if f is even, and I want to take the integral from -a to a, what do you notice about the area on each side of 0? They're the same. So I could instead just take the integral from 0 to a and double it. Every even function, if it has y-axis symmetry. Yeah, it's got to have y-axis symmetry. If f is odd, which means it has origin symmetry, and I want to take the integral from -a to a, what do you notice about the area on either side of 0? They cancel each other. Yeah, they're exact same area, but one's above the x-axis and one's below. So that's my favorite kind of integral to evaluate. you don't have to do anything. Just write down 0. Okay, so another application of integrals is being able to find the area between two curves. So if I have two functions, f of x and g of x, for now we're just going to assume that f is always above g, but the result will hold even if that's not the case. But it makes it easier to visualize when we picture it this way. Okay, so how would you find the area A between the curves f and g? Yeah, so I could take the area under f, right? That would be all of this area. And then subtract the area under g. Subtract this all off, and all you're left would be the area between f and g. So I would take the integral from a to b of f of x and subtract the integral from a to b of g of x, which is the same thing if you wanted to. You can do it either way. You could also just evaluate one integral of f of x minus g of x. Those are equivalent expressions, so you can do whichever way you want. So take a couple of minutes. Find the area between x squared and radical x. On what interval? That's a good question. The bounds are going to be defined where those two curves intersect. Right? So like if we draw a picture of it, x squared looks like this, and radical x looks like this. So there's really only one piece of the plane that is between the two curves that has finite area, right? Like we could be thinking about this, but there's infinite area there because they're just getting further and further apart. So really the only place where we could be finding the area is this. So what is that point? Where do those two intersect? 1. Yeah. 1 squared is 1 and radical 1 is 1. They're equal at 1. So the interval would be 0 to 1, yes. All right, which curve is higher? Which curve is the bigger between 0 and 1? Root x, yeah. So I'm trying to find, my interval is from 0 to 1. I'm trying to find the area between these two curves. The bigger curve is root x. That's the one that's above. Okay, so I'm going to subtract all the area under root x. Here's all my area under root x from 0 to 1. And then I'm going to subtract off the area under x squared. And that will leave just that green area, which is what I'm looking for. So take the integral from 0 to 1 of root x and subtract the integral from 0 to 1 of x squared dx. And I'll just do these two on my calculator. Or I could do just one single integral from 0 to 1 of root x minus x squared dx. They should come out the same. So it kind of depends on what kind of math personality you have about which one of these you would do. If you have sort of a start from the picture and use a visual kind of thing, you might be more likely to use this first equation. And if you are a more I like to do the most efficient thing possible kind of math person, you might just do a single integral like this. And one is not better than the other. They are equivalent. Math. Fine, thank you. Square root x, comma x, comma 0, comma 1. Looks like 2/3. And then we're going to find the area under x squared from 0 to 1. One-third. And I'm making an educated guess that those are rounded fractions. It's possible that they're not, right? But I'm just making an educated guess based on seeing 0.33333333333 that that's really a third, and my calculator just can't deal with that. So it looks like my total area would be a third. So let's just, to double check, show that if I do it all in one integral, I get the same thing. So I'm going to do square root x minus x squared. Looks like it's a third. My calculator is doing this numerically. It's estimating using a lot of rectangles. So I'm not getting, so my educated guess is that this is exactly a third, and my calculator is getting a very close number to 1/3 because it's estimating. All right, so that brings us nicely to this last thing of the semester. Really important results that we will continue talking about in Calculus 2. If you know the answer because you've taken a calc class before, please don't say it out loud just yet. Suppose we want to find the integral from 0 to 4 of 4t cubed dt, but we're stranded on a desert island without our favorite graphing utility. So we've already seen that finding the area under a derivative function tells us total change, right? The integral of a rate of change is total change, right? So the area under a velocity curve is distance traveled or displacement. So we can imagine that 4t cubed is a derivative function, right? So if we could think about f prime of t as 4t cubed, that it's a derivative of some unknown function f. So 4t cubed is the derivative of some function. If we could magically come up with what this function is, what function has as its derivative 4t cubed, then evaluating this integral would be simple. So sit for a minute and try to think of a function that has a derivative of 4t cubed. Once you've experienced your miracle, check with your neighbors and evaluate the integral using the f that you come up with and the fundamental theorem of calculus, and also with your calculator. Okay, so what function has as its derivative 4t cubed? T to the fourth. Or, Kevin, what other function has as its t to the fourth plus 8, right? Because the derivative of the constant is always 0. So you can pick, there's actually an infinite number of functions that have as its derivative 4t cubed. The simplest one is t to the fourth. Just take the constant to be 0. But you could pick any of them. And I'll show you why. So if I want to take the integral from a to b of 4t cubed dt, if that's an f prime, then this would be equal to, sorry, what are my limits? 0 to 4. That should be equal to f of 4 minus f of 0. So if f prime of t is 4t cubed, then that means that f of t, first we'll just do it with t to the fourth. We'll show that it works with t to the fourth, and then I'll use Kevin's t to the fourth plus 8. Okay, so f of 4 would be 4 to the fourth, which is 64, minus f of 0, which is 0, and I get an area of 64. Is that true? Is 4 to the fourth 64? 256. Thank you. $256. So let's double check this on the calculator. Um, 4x cubed comma x comma 0 comma 4. 256. Good. So your calculator is doing this by using a lot of rectangles to evaluate that integral. We did it using the fundamental theorem of calculus, okay, knowing that the integral of a rate of change is total change. All right, but what if I had chosen a different function, f, that also has as its derivative 4t cubed? Would this still work? Okay, so f prime 4t cubed, I could choose as f 4t cubed plus 8, right? Or, oh, yeah, thank you. T to the fourth plus 8. Right, because the derivative of t to the fourth would be 4t cubed, and the derivative of the 8 is 0. So it also has as its derivative 4t cubed. Well, let's see what happens if I plug 4 in there. I get 256 plus 8, which is 264. Right, and when I plug a 0 in there, I get 8. And 264 minus 8 is 56. Same thing. So you can pick any function that has as its derivative 4t cubed, and you will get and use the fundamental theorem of calculus, and you'll get the right answer. Usually, we just pick the simplest one, right? So t to the fourth, just because it makes our calculation a little bit easier.